All right, this is still integration, what you've been doing, the fundamental theorem of calculus, where you plug in values, find area. Remember it's kind of a two-step process. The first step is finding the antiderivative. And when you first did that assignment, that's all you did. And then the next step was plugging in to get actual area. So we're going to kind of go back and do that again with the first step, finding the antiderivatives. Now, if you remember the chain rule, I will say those of you that did the little U substitution over on the side and didn't do the shortcut typically do better on integration with substitution, okay? And I'm one of those that did the shortcuts as well. So what we're doing is we're finding the reverse of the chain rule. So if you remember the chain rule, we took the derivative of the inside and the derivative of the outside. So what that means, working backwards, how you would know when you have to use substitution is you're going to see two factors. All right, so it's a product of two factors, the derivative of the outside and the inside. So what we do is we let u be the inside, which is kind of the same thing you did when you were doing the chain rule, and then du, okay, so is going to match the outside function. Now this is going to actually match the dx part, and as you can see here, the dx's are going to cancel, right? So again, a lot of students really struggle on this section, so this might be something you might have to go through lots of my examples. It's usually fairly easy, again, to find an inside function inside parentheses, under a square root, cube root, in the exponents, or a little bit more difficult is the denominator. So what we want to look for is we want to find our expression, our g of x, okay, within our integrand, that integral that we're setting up, and we set it equal to u, and we call this the inside function. Then typically, you'll see sometimes you have to manipulate it. The outside function ends up being the derivative. And so we start doing this substitution where we substitute to make something easier so we can evaluate an easier integral, and then we have to substitute everything back. All right, you ready? Let's do it. So when I look at this, my first question would be, how do I know this is substitution? Because it says, make a substitution. That's funny, right, Cindy? Yeah, no, that ain't funny. The reason why is I see two factors. I see this e to the x squared, and I see the 2x. Remember, the dx is just telling you the variable of interest. So what I'm going to do here now is I'm going to use my substitution. As I can see, this is an exponent one. What I would substitute in this case would be my x squared. Okay, so my x squared would be what I'm looking at. And so just kind of over here on the side, I say let u equal x squared. And then when I took the derivative, I wrote it, take the derivative of this function u with respect to that variable x. The derivative now, bring the 2 down and subtract 1 from the power. And I can multiply both sides by dx, because what happens when I do, that cancels, and then I end up with just du equals 2x dx. Notice, and this is the big deal, that matches this piece exactly. And that won't always happen, but on these first few examples, that will happen, okay? So using this substitution method, then, what we're going to do is we're going to take our, let me just rewrite it here, our e to the x squared times 2x dx. I want to find this antiderivative. I'm going to do this with substitution. I let that piece equal u, and when I took the derivative, this piece equals du. So here I go. I'm going to substitute e to the u du. Notice now this is something very easy to find the antiderivative. The antiderivative of e to the u is just e to the u, and then of course plus c. And then finally, your last step is you substitute u back. So e to the x squared plus c would be the antiderivative of this function. How do I know that's right? Check it. The derivative of e to the x squared is e to the x squared times the derivative of x squared, which is this piece right here. So this is just kind of weird because you're doing two different things. You're doing derivatives over on one side, substitution, antiderivative, substitute back. And those are pretty much the steps, as you're going to see, you know, when we go through these steps. That's pretty much the steps on how to do these. Now, I'm going to do a couple of more examples, and they're going to seem weird because it's going to be like, wow, all of these have the same du, but that's just because these are the examples that I picked right away. Okay, so they're not going to always be that way. All right, so what do I mean? So looking here at this piece, I can see it looks like it's very clear that I can see what the inside would be, right? Because the inside is inside this parentheses. So the inside is what you let u equal. So just over here on the side, I say u equals x squared minus 3. Okay, I only take the inside, I don't take that exponent. And then we take the derivative with respect to x. The derivative is 2x. The derivative of minus 3 is a constant, so that's 0. I multiply both sides by dx, and you're going to see this step we typically get where we skip, and we just say this is du equals 2x dx, and guess what? That's that piece exactly. So over here for my substitution, again, let's rewrite it. X squared minus 3 cubed 2x dx. This piece becomes u. This piece becomes du. So rewriting it would be u cubed, and then that piece is du. How do you find the antiderivative? 3 plus 1 over 3 plus 1, and of course plus c, which would be u to the 4th over 4 plus c. And then finally, your last step, substitute back what u equals, x squared minus 3 to that 4th power over 4 plus c. And as I mentioned, if you would take the time, so this is the answer, if you would take the time and find this derivative, right? Remember how we'd find the derivative of a chain rule? The 4 on the bottom just stays the same. I would bring this 4 down front. I subtract 1 from the power times the derivative of the inside. And notice that gives you this back. All right, so all of these with the substitution, it might, I'm guessing right now already, it takes you a little while, it's already confusing. You're gonna have to work a bunch of these. And the whole question always is, why am I doing this over here to make your integral a lot easier? That is the whole point you're doing this. All right, let's see one more. That was the same one. All right, so if I look here, then I am going to automatically see that I am going to pick the bottom, the denominator, to be u. So x squared plus 4. This is where I said we typically skip that dividing by or multiplying by dx, because I already know it's going to be 2x and then the dx. Now, I know what you're going to ask, why are all of these 2x dx, because I wanted to repeat a lot of the same problems over and over and over until you finally see what we're doing. All right, so now over here, 1 over u du. What's the antiderivative of 1 over u? Are you yelling, Cindy? Cindy, I know. It's ln of u. And then finally, ln of x squared plus 4. I'm just absolute valuing to make sure you're taking the absolute value of a log. And now from here, I could, again, if I took the time and took the derivative of that, the derivative of ln of anything is 1 over the anything times the derivative of the anything. And so I do get this piece back. All right, now a lot of the questions are always, why are you doing this substitution stuff over here? And I did mention it is to make it easier, but here is the real reason. If you substitute this piece right here, and we've been calling that the inside piece as u, this makes absolutely no sense. I want to find the antiderivative of u with respect to x. That's how you read that. That makes no sense. That is why we are having to do the substitution. Okay, so that is the big key. Why do we have to do our substitution? Because we have to make our variables match. All right, we're going to do a lot more examples, and notice that this is just the first step of finding the antiderivative. We will then go into finding area with the fundamental theorem of calculus.